Okay, it's 8:30. So today we will have today's the 5th day of the summer school, and we will have 2 lectures on chromatic homotopy theory, both given by Guchuan from Michigan University. And the first talk Guchuan will be telling us is about Quillen theorem on pi star mu.
Yeah, thank you for the introduction, Hannah. And yeah, it's really my pleasure and honor to speak in this summer school. Okay. Yeah, so today's topic is Quillen's theorem on homotopy groups of mu. So at the opening talk advertised, so asking the right question can reveal orderly or periodic behavior among the parent chaos of all the homotopy groups. And the starting point of this picture is from the deep relation between the homotopy groups of mu and the formal group laws. And that's today's topic. Okay. So maybe let me reveal something from yesterday. So in Yutao's lecture, we learned that, or this is also happening in the opening talk, for a given complex-oriented commodity series, maybe more precise, you want to also choose orientation. So then you can assign it a formal group law. So more precisely, so if I'm having a complex-oriented theory, then by definition, I got the isomorphism once I have made my choice of the orientation. Then the cohomology of the complex projective spaces is a formal power theory on one generator. And moreover, if I think of the product of 2 copies of CP infinity, this will be formal power series on 2 generators. So there is a multiplication of spaces like given by tensor of bundles. It induces a map on the cohomology, the other way around. So all this data allows me to define a formal power theory in pi star of E with 2 variables x and y. So the way I just defined this one to be the image of the orientation for E itself, T. So notice there's a map. So in particular, the element T maps to some elements downstairs, which is just a formal power series in the 2 variables. Okay. So this is how I can assign a formal group law to a complex oriented cohomology series. Okay. And later, in Zhipeng's talk, so we learned something special like about the complex coordinate theorem, which is the key player or the central player in the whole story. So namely, this guy, the complex coordinate theory, is a universal, or itself is universal among all complex-oriented cohomology series. Okay, so what does it mean? That this is just saying if E is a complex-oriented cohomology theory, So again, I'm secretly already make a choice of the orientation. So then there exists a map from MU to this guy. And this is a map of ring spectra. In particularly, the orientation of E is just given by the orientation of MU push forward. So I can define this one where this TE is F star of is F upper star of this guy. Okay. Yeah. So then a natural question is asking, okay, so if I know MU is special among the complex oriented commodity series, so if the formal group law associated to MU also universal in some sense? And the answer is yes, and that's exactly the Quillen theorem, and that's today's topic. This is the Quillen theorem on high star MU. But I wanna make a warning. So this is not the historical. This is not the order how people discover all these phenomena. And in fact, like it's Quillen first observed this deep connection between the formal group laws and the complex cobordism theory. And then they have the story like following. And that's the starting point for this beautiful story, like go back forth between the algebra and topology. So this theorem is really something surprising, like when it's first discovered. So it's reveal a deep connection. Okay. So now maybe first questions should be or like what happened is before Quillen discovered this theorem, or even before like the complex cobordism theory, algebraists already study formal group laws, and so the universal formal group law. So particularly it's over a ring. Let's denote L, since this is studied by Lazard, and like the theorem of Lazard is to identify what exactly this ring is, and so the ring is called the Lazard ring nowadays. Okay. So then, like the theorem, our theorem is actually seen from the universal formal group law. Because if we will say for any formal group law over a ring, that's the same data as a ring map from the Lazard ring to this ring, and the push forward for the universal formal group gives this formal group. And the MU, there is a formal group associated to this complex oriented theory. So it admits map from the universal formal group law, the Lazard ring. And the theorem is this is an isomorphism. Okay. And the outline of proof is homotopy groups are in general hard So what we can do is we can compute something easier. So we'll compute the homology, which is much easier. And this is also done in Zhipeng's talk last time. So we compute the homology of MU, and it's a polynomial ring on these generators. So then the outline of the proof, we will make such a community diagram, and then we will trace the diagram to see the isomorphism of theta. So the outline for today's lecture, the first part, we will introduce the universal formal group law over the Ladar ring, and we will also explain the map from the Ladar ring to like the ring which is isomorphic to the homology of MU. And second part, after that one, we will have two explanations for this ring. One is from the formal group law point of view. The other is from the homology of MU, and we'll explain why they're exactly the same. So I use an equation downstairs. And then in the last part, I'll outline how one can compute the pi star, like the homotopy groups of MU, from knowing the homology of MU. And then like outline the proof, like running the diagram, like to see theta is a isomorphism. So later on we will see like both vertical lines will be isomorphism after tensor with the rational number Q, and trace the image can prove theta is isomorphism. So that's a plan for today's first lecture. Okay, yeah, so now let's start. So the first one is the universal formal group over the Ladar ring. This is formal group law, and it's over the Ladar ring L. So maybe let's first recall what is a formal group. So a formal group F, maybe let me read over, so there's no confusion, over a ring, community ring R. So this is just a, well, it's just a formal power theory. In R coefficients, such that it satisfies some conditions, which just comes from like, what do you think about the group? So it commutes and it's associative. Okay. So from the definition, it's easy to see. So what sort of data I need like to make this happen? So it's a formal power theory. So I can write it. I can write it out in detail. So it's just a formal power theory with coefficients, and these coefficients are all in the ring R. So, but it cannot be any formal power theory. It must satisfy those equations. So in particular, there will be some requirement. Of this AIG. In other words, it satisfies some relations. So then from this one, like if I'm trying to make a universal one, in the universal case, I mean, so I'm hoping there's a universal one in the sense, so this is my, maybe also use F, I mean just universal. So over some ring L, like So let me spell the details for the definition for the universal here. It's saying given any formal group law G over R, then there exists a map, ring map, ring homomorphism from the third ring to this ring, such that G is just the push forward of my universal formal group. So this is not hard. So how can I cook up this my G? So I only need to know what's the coefficients for G, and that's just I need to know the value for this AIG. So once I know the value for all this AIG, I automatically have a map from the ring C drawing this generator's AIG to my ring R, and that's exactly the third ring. So the naive, or like the first easily to say is just like this, drawing all this AIG, but you wanna quotient the relation. So the relations are coming from these conditions. Because my formal group law satisfies some equations. If I write out the coefficients, so my f x, my universal one over there, it's just x plus y plus this guy. And if I plug in this formula in the above conditions, I will end up with some equations for AIG, and that's the relation I want to quotient out. So in this way, by construction, it automatically will be the universal one among all the formal groups. But this won't make it like a theorem named after some people. So the actual theorem is saying, okay, so this one defines a universal one, but well, the third proof is the following. Like upstairs is like generators with a lot of huge amounts of relations, but the third say this is actually torsion free. I can choose bases such that it's just isomorphic to a polynomial ring on generators xi. And for the purpose, like we will see in the end, this is the homotopy groups of MU. So maybe let me assign some grading. Now, like instead of just a formal group over ring R, it's over graded ring. So let me assign the grading by as follows. I'll set the degree for x and y both to be -2. So then I hope everything lies in pure degree -2, because the first two terms is x plus y. Then this AIJ will live in degree I plus j minus 1, the whole thing times 2. And if I using this notation, then my xi will live in degree 2i. Okay. Yes. So I will outline the reason why you would think this is actually true. But also this is a non-trivial theorem. There's some hard algebra you need to do. So I will hide all those hard part. So maybe let me write the reference for this one. So later on, like so Lurie has a notes for chromatic homotopy theory. So chromatic homotopy theory. So this one can be seen in lecture 2 and 3. So later on, this will just be L2 and L3. And also, Doug Ravenel has a great, has a so-called green book let me recall the name for the green book. I think it's complex cobordism theorems series and the stable homotopy groups of the sphere. Okay. Yeah, so this is like the theorem in the appendix. So
there's no theory. Complex cobordism and stable homotopy groups in the sphere.
Oh, complex cobordism theory. And oh yeah, so there's already the, yeah, thanks Hannah. Oh, and also I missed a question. Is there any way to describe xi in up to higher terms? Well, like by degree reasons. So you can start with x1, which is degree 2. There are not much choices of aij there. But then as the degree goes higher and higher, the formula is much harder. Yeah. Okay. Right. So right. Let me put the number of the reference first. So this is, yeah, feel free to stop me and type question. I'll try to keep an eye on the chat. So this, well, the statement is in the first one, but like the key step, the hard step is 2.1.12. Okay, but in this lecture, at least let me like present something to convince you this is true, and maybe also like partially answer the question. Maybe instead of knowing exactly how it works, I'll do a easier version, which I'll map to. So this is as promised. We will also not only introduce the third ring, but also introduce a map to this ring Z, drawn with B1 all the way to BI. So there is a map, and this one such that after tensor with Q over character 0, this is an isomorphism. Okay. Okay. And let me explain how to construct this map. So the first, there's observation. The observation is like we're talking about formal group laws. So maybe it's good to first at least have a concrete formal group law, so we can think as an example when we talk about it. So the easiest one is the additive one. So I just choose my formal power theory to be x plus y. Okay. So this automatically satisfies all the conditions it asks for. So then notice, maybe I want something more interesting, because this looks like a boring one. So how can I cook up a new one from this one? So notice that another observation is if I'm giving a formal group, giving a formal power theory, which is invertible, let me just make it easier. So I just like the first coefficients to be 1, which is invertible. So in formal power theory, if the leading term is coefficients is unit, then it's invertible. So in particularly, if I'm giving such formal group, such formal power theory, so this one in particular, this one is invertible in the formal invertible in the formal power series over this ring. So I join out the BI as my coefficients. So G inverse X exists. So an easy fact to check is, then I can define a new formal group law by doing the following. So I change my coordinates. Instead of using X and Y, I use G inverse X and G inverse Y, and I apply G outside. So this is also a formal group law. That means it satisfies all the conditions I ask for. So in particularly, in particular, I can construct G inverse X plus G inverse Y. I start from my easiest additive formal group. I can construct a new formal group by this way. And this is over the ring 3 with B1, B2, and so on. Okay, now I have a formal group law over this ring. By the universality of the third ring, I automatically have a map. That's our map phi from the third ring to this ring. Okay. So then the proof of the proposition actually follows very easily from the following fact. We will talk about this fact in next lecture, focus on formal group law. But let me just state as fact for now. So if I'm in the situation character is 0, which is Q, Q is the case, rational is the case. So all the formal group laws is actually construct as above. Namely, is from the additive one, which is just X plus Y by a change of coordinates. By the change of coordinates, I'm just saying I'm doing the above. I'm pick up a formal power theory, invertible one, and with all these coefficients. So I do the above. I just do G inverse X plus G inverse Y, and then I apply G outside. So that will recover everything. So then you can believe if this is true, that is saying like all the formal groups are given in this way. So in particularly, if I map from the universal one to this one, that will be an isomorphism. So this okay. So this one indicates the map above is an iso, it's an isomorphism. If I'm in the case character 0, which I can make this happen by tensor it with Q. So after rationalize, this is true. Okay, yeah. So this like the at least you have seen this one can maps to a torsion-free free ring, and what actually makes it's actually itself is of the form like free on generators x1, x2, and so on, is following from the following fact. So this is a we are now proof. Yeah. This is a slightly harder fact. So I know this is a isomorphism after rationalize, and I can think of the indecomposable part. Now I can define I, which is the ideal. This is like of all positive filtration, positive degree. So this is consists of elements of positive degrees. So that's my ideal in L. And similarly, I can define G in the other part. But this part is very easy. You can see directly all the positive ones are given by these BIs. So think of the indecomposable part, which I can write algebraically as I quotient I square and G quotient J square. So this one is easy. This is just like if I'm concentrate on 1 degree, this is just generated by one copy generated by Bn, one copy of Z. And the harder fact is the map phi maps this one like phi is an injection. So in particular, this indicates the original map is an injection, and moreover, I also know the image. So the image is p times z if n is of the form p to the k, p to some power k minus 1, and if it's else, then it's just the image is copy of z. So you say after rationalize, like p is invertible, so it's iso on every degree, but before it's only iso on the degrees, it's not of the form p to the k minus 1. Okay, so this is a harder part we will not prove. But once you assume this fact, then it follows like the original ring must also be a torsion-free ones and on generator xi. And you can particularly choose xi such that the image of xi is bi in most degrees, and in those specific degrees, it's p times bi. Okay, so that's the first part. And now, just as like I said before, so if I'm thinking of this ring, now it has two explanations. One is from the formal group law point of view. So it's basically coming from a coordinates change. It appears in those coefficients. Also, recall yesterday we compute cohomology for mu, and this is also the answer. And in particularly in that case, like this BIs is really coming from, if I thinking originally, I'm taking the homology for Cp infinity, and in here I got generators beta I, where my beta I is corresponding, is due to the generator T to the power I. We'll just recall like the cohomology is one generator on T. Yeah, if you want, you can put formal power series, doesn't change. Okay, so that's how we define those beta I, and those will be, in the end, becomes those BIs. So these are like two very different explanation, and why I put an equation at the beginning. So here is an explanation from the formal group law, like how to relate these two. So maybe it's useful or it's helpful to work in a more general case. So in the end, we want to explain this one. So I can work in a more general case, pick up any another complex-oriented cohomology theory, and turns out the same thing happens. And the BI can be explained in the way as a coefficient of the change of coordinates. So the way to think about this one, if you notice, so this one is just pi star E smash mu. And this one has two orientations, or at least has two obvious orientations. One is from E. So as we explained at the beginning, mu is universal from all the complex orientation. So like the orientation can also comes from a map from mu. So E itself is complex oriented. So I can have a map from mu map to E, and this is the same as E smash S naught, and I can use the unit map the S naught to mu. So the computation gives an orientation of E smash mu. However, I can also use the orientation on MU, which is just mapping MU to MU itself, take the identity map, and do the same trick. I can smash a copy of unit sphere, and everything is in spectra, so there's a unit map, so I can have another orientation. And as a consequence, if I'm thinking the cohomology of CP infinity, this is isomorphic to the formal power rings over the coefficients. But on two different generators. So by the similar proof as Zhipen presented, like one can prove this one is of similar formula. It's pi star E, drawing all these BIs. And now I have a isomorphism from the left-hand side to the right-hand side. Again, so I can write my generator TMU in terms of TE. So this will give me a formula. There's some formula makes this happen because the isomorphism. And the claim, so this AI is in the rings, in the coefficients ring, which is this guy. The claim is AI is just BI. That's why I put the equation, because in this interpretation, these BIs are just like as a chain of coordinates. In particularly, in my case, I start with the cohomology of MU, which is HF2, or like if you work at the or HC, smash MU, and over the ordinary cohomology, the formal group associated to that one is just an additive formal group law. So I'm changing the coordinates from an additive formal group law to another one, and this is exactly the BI interpreted from our formal group law point of view. And on the other hand, it appears this one, it comes from the coefficients ring, which is just a cohomology of MU, or the E homology of MU. So this is the claim like makes like in the square, like the bottom is a equation. So these BIs are the same in the proof. Yeah. So let me just outline and explain a little bit more for why this is true. So this is in Lurie's lecture notes in 7 if you want more details. But let me just say the way you should think about it is you want to think all of these ones as certain maps. So this one can corresponding to a map. So a complex orientation is just an element in the second cohomology of CP infinity, which is the same by Tom isomorphism is a map from MU1 into this cohomology. And so once you have this map, then you can produce a E module map. That's the same information. If I know how MU1 goes to there, if it's E module, then I can just smash E both sides. So I will have an E module map from MU to this guy. So in this case, the orientation from MU, just by construction, maybe it's better for me to put E on the same side. So you can see this is just MU1 includes in MU like canonically, and the whole thing smash E is given the map. So the way I think it as the E module map has an advantage. So the advantage, maybe let me put it here. So the advantage is after smash with E, this one splits. It's very, because like I know like E star for MU1 or E upper star for MU1. So this one is just a wide sum of all the even dimensions suspensions of E. So in this way, you can write. You can think TMU is really the sum of some maps because it's a wedge outside. Well, similarly, you can think E as also as a map. So how does this one maps? So since this one, I can also first MU just maps to E, and then E maps to MU smash E, right, as we described. So this one I can also make an E module map as MU1 smash E into MU smash E. So this can be called like corresponding to phi E. And then like I can also think of the BI now can have the interpretation of the as a cohomology generators. So it's just a map from the sphere into here, which I can also make an E module map and smash E on the left-hand side. So then I know like how can I do the how can I form the map for the MU orientation? So what I do is just I need to first MU1 smash E. So this is many copies, right? So I need to projects to one copy among all these copies, and in that copy, I did use the map like BI maps to this guy and use the orientation of MU there. Sorry, the complex orientation on E there. So this will maps to this guy, this B and in the orientation of E embeds there. So from this point view, you can see in fact, this will be the, MU will be the sum of this one. Like the projection can be considered as a map to the power I, and then inside will be BI, and there will be the TE there. So in the end, it becomes this phi E. This form the formula. This T will be combined together to be I+1 and BI plus T. So this is a very rough outline proof for the fact that AI equals BI. So the upshot is, so like all this one, like when you have E smash MU, like using this identification, they have the meaning. This is exactly the coefficients in the change of coordinates, and this will shows up like later on in the next talk. Okay, so this is step 2. So in the remaining time, let me outline the last part. Like for one method, we will come back with a point value from the formal group file next lecture. But now let's just say the third part is I want to compute pi star the homotopy groups of MU from the homology of MU, and this can be done by the so-called IDM spectral sequence. So I think we don't have time to expel the details for this one. So this we can do it one prime at a time. Okay, so maybe let's say we are at prime P, and then it's P homology of MU. This way, this will converge to or maybe P localization. So this is a form of the IDM spectral sequence. So we won't have time to spell the details, but the point is you have something algebra as the data, as the input data, and you figure out something geometric happening. In the end, you have something topology or geometry as output. And there are a lot of algebraic gadgets appears that will matters later on. So this A lower star is a dual of node algebra. So which is also the HFP homology of HFP itself. And in the all prime case, this is C1 and C2 and so on. Tensor with the extrinsic algebra on another set of generator tau s, where Ci is of degree 2 times p to the I minus 2, and tau I will be in degree 2 to the I minus 1. So this is a complicated formula, and yeah, so I don't expect so like people seeing it first time to follow. So the point is like this one is not only an algebra, but it's also a co-algebra with some compatibility. So it's a Hopf algebra, and everything like the left-hand side is computed in the co-module category over this A star, but it's purely algebraic. So we can do some computations, and in general, like spiral sequence is hard because it's not done like after you compute the algebra data, you need to figure out something geometric information to compute the final data. But in this case, we are lucky because of the just for degree reasons, just given for free, there cannot be anything tricky happen in this case, and it turns out it computes the end of the result. But let me just point out, like if you really wanna do this by yourself, what kind of machinery you need if you wanna finish this proof, like from the classical method. So what you need is the following. So like Zhipeng compute this guy, but it's not good enough for this one. As we said, the left-hand side, everything, the cohomology algebra is computed in the A star, like the co-module category. So in addition to knowing the ring structure, you also want to know the co-module structure. So maybe, so here, everything is from the green book. I just copied here, like, so just for reference, if you want to really compute by yourself, the first thing you need is you want to define a cotensor, which is just like something mimics a tensor, but it's in the co-module case. Once you have the cotensor, what's important is you have a structure theorem. And the point is, once you apply in the structure theorem, you will notice that let's call the even degree part, like this part is P star, and let's call this E star. So you realize the co-module structure on H star mu is really only comes from the even part. It's P star co-module. So and moreover, this guy is isomorphic to like write down explicitly all the UIs for I is not P to the power minus 1. This guy tensor with so this is a so you apply this one, you can see this is in the end this one is P star tensor with this algebra applying this structure theorem. So this one tells you what's the co-module structure H star mu admits in this case. So in particularly so after this one, like you got the structure enough, you can carry on the computation, compute the EXE group. The one last step is with this structure theorem, you you kind of observe that the computation can be easier. Instead of computing over the large co-module, more complicated co-module structure, you can compute over a smaller one. So in the end, you use a theorem called the change of ring. So the upshot is the following. So over the full dual node algebra, maybe it's complicated, but this one can be computed over a much smaller part, only the exterior part, the E star. And so in this, if you apply the structure theorem, this is part of C. Let's denote it by C. So after the chain of ring, this part can be replaced by C. This is applying this one. Well, like C is evenly concentrated, E star is all concentrated. No, sorry, E star, like the generators are all in all degrees. So the action is actually trivial. So this is just FP. And then tensor C outside. And this one, like you can compute by hands, and that gives the answer. So in the end, you compute the E2 page. And it turns out to be a polynomial algebra on those generators for this UI. For I, it's not of the form. And also for some cohomology generators. I use G, so let me use K. And then next, you have the corresponding degrees. So the point is, this one is filtration 1. It's sort of important. But in the end, like, so with all of this one, if you follow the structure theorem and the co-module cohomology algebra, let me just put the upshot. Like the answer is you can compute this guy to be Z just on generators x1, x2 in even degree. And moreover, because you compute from the H star mu, you can look at the map, and it matters, like these guys are in filtration 1, and this is filtration 0. So in the filtration 0 part, like xi goes to bi. And in those part, which is not U, but because Z is, or the epsilon J is a generator of that column. So then this is degree is not P to the I, P to the K minus 1. In those degrees, it's P to the K minus 1. This goes to P times B times I. And you look at this formula, you see this one like a while ago, and that's what happens on the left column. So if you now, like, if I piece everything together from 1 to 3, so I got the third, from the third ring, I have a map to this guy. And now both sides I know it's of this format. Maybe I should use Y1. Okay. And so I know this one can map to this guy, which is just the homology of MU. And xi, so after tensor Q, this is ISO. After tensor Q, this is ISO. And if not tensor Q, if I'm looking at the non-degenerate part, like I defined before, in those parts, I know the xi goes to bi, which equals bi, and this is yi, so it's ISO. In most cases, if this is not the Fourier degree, otherwise it's P times bi. and it also matches up. So it's also on top. So basically that's a proof. And I know so the last part is very technical. I didn't say much about the co-module structure and so on. And I didn't tell you anything about the structure theorem. Where does it come from? So in next lecture, we will review this whole part, like the last part, from the formal group law point of view. So then it will be like much more intuitive, like to think about it. Yeah. So that's all for the first lecture.